Greetings, everyone. Lesson 4 in our pre-cal. We're going to talk about symmetry, not the same kind of things you talked about in like your geometry class or whatever like that. We're going to go into more of an algebraic definition of symmetry, and let's go ahead and get started. 5 terms I'm going to want you to know: y-axis symmetry, x-axis symmetry, origin symmetry, even functions, and odd functions. I'll cover those as I go through, and then you can leave yourself a little bit of space here and go back and write those down later. So to begin with, let's start with a basic, parent function here, your quadratic parent function, graph of a parabola right here. And if you take a look at it, it is a formula of the, or it is an equation of the form y equals x squared. And pretty sure you're familiar with this graph by now, what it looks like. Now, my question to you is, remember when you talk about symmetry, you're talking about some line, some point, some whatever that cuts it equally in half. In this case, it appears that this cuts it in half. And this line has a specific name that is your y-axis. So I can tell you that the graph of y equals x squared has y-axis symmetry. Now, this is kind of what you would have done in your geometry class, or maybe in an algebra class or something of that nature. I want to go beyond just the look at the picture and whatever, because I want to be able to do this without graphing, without calculators and such like that. So I want you to examine some points here. Notice that in this particular graph, the graph of y equals x squared, which has that y-axis symmetry, contains the point 1, 1. Its reflection right over here contains the point -1, 1. So same y value, but the signs on the x's are different. Okay, let's keep that in mind as we go further. This y-axis symmetry graph contains 2, 4 and -2, 4. Again, the y value stays the same even though the x changes coordinates, changes signs. Likewise here. It contains the point 3, 9. It also contains -3, 9. So the lesson I hope you're getting from this y-axis symmetry is not just the y cuts it in half. I hope you're seeing that when you replace x with -x, it has no impact on the y value. Whether I change 3 to -3, 2 to -2, 1 to -1, just changing the sign does not change the y value. So we replace x with -x, and the y is the same. That's the idea or the concept I want you to get a handle on. So go ahead and feel free to write this down if you will. A graph is symmetric with respect to the y-axis if, whenever the point x, y is on the graph, then -xy is on it. In other words, in algebraic terms, that means, like we just got done talking about, if you replace x with -x, it gives you the same y value. It preserves the value. Okay? Let's take a look at this graph. X equals y squared. And if I go ahead and draw that, here you go. Again, forgive my lack of artistic talent here, which is why I graph it on different computer softwares. Is there something that cuts it in half? Answer to that, yeah. This time, this horizontal line that I've outlined in blue cuts it in half. In other words, x equals y squared has x-axis symmetry. Okay, I emphasize again, yes, I understand you can look at the graph and do like you did in geometry, but I want you to get to the point where I can give you some creepy, weird equation that you may not know the parent function graph for, or even have access to graph it, or you may not even graph it. I want to be able to tell by the x's and the y's, by the coordinates. So again, 1, 1 is on the graph right here. Its corresponding reflection is 1, negative 1. 4, 2 becomes 4, negative 2. So what happened this time? Well, in this case, the 1 and the 2 changed from negative 1 and negative 2. So in other words, for x-axis symmetry, you change the y into negative y, and the x stays the same. So in other words, when we're talking about y-axis symmetry, if you change the x with negative x, it has no effect on the value of the function. For this x-axis symmetry, when you change y with negative y, you still get the same result. So here's your definition for x-axis symmetry. Again, if the graph contains xy, it also has x negative y, meaning change the y, the rest stays the same. And like we said, if you replace y with a negative y, it's equivalent either way. Third type of symmetry. I have the graph of y equals x cubed, and let's look at points here. 1, 1, negative 1, negative 1. 2, 8, negative 2, negative 8. In other words here, you change the x and the y. So if I have 1 comma 1, so if you change the x, the y changes too. If you change the 2 to negative 2, well, it changes the y as well. That's what happens, or what is called origin symmetry. And if we examine it, again, to be symmetric with respect to the origin, if it has xy, then it should also have negative x, negative y. In other words, not only do I replace x with negative x, but I also replace negative y for y. And that will give you that equivalent expression. Okay. Couple of more definitions, the last two. An even function, by definition, an even function has y-axis symmetry. Now, if you remember, we talked about y-axis symmetry means you change x for negative x, the y stays the same. Same thing's true here. An even function has y-axis symmetry. An odd function, you might say, well, okay, that's x-axis symmetry. No, because x-axis symmetry isn't even a function. It doesn't pass the vertical line test. So an odd function has xy and negative x, negative y. In other words, an odd function has origin symmetry. You replace x with negative x, like here. If I change the sign of the x, it also changes the sign of the y. You know, remember, f of x is y, so that's the basic idea. That's the terminology. And again, here's a little bit more formal definition and also an example. Here's an example of an even function. And again, an even function has which type of symmetry? Yeah, it has y-axis symmetry. So here's an example. X to the fourth plus x to the squared, and that equals your f of x. So to determine algebraically if it is an even function or if it has y-axis symmetry, I'm going to replace this x and this x with a negative x. And hopefully you recall from your algebra days that when you take a negative and raise it to the powers and they're even, that it's going to turn positive. A negative raised to an even power will turn positive. So what do I see? I see that changing the x with the negative x gives me the exact same thing that I started out with, which means it does have y-axis symmetry, which means it is an even function. Likewise, here's a little more formal definition of an odd function. And if you take a look at it, again, here is your f of x, and it's x cubed plus 2x. And again, I'm going to replace the x with negative x. And let's see what happens with the y's. Well, I get this. Is that exactly the same thing that I started out with? No. But what that is it's the negative of x cubed plus 2x. In other words, if I change the x's from positive to negative, it doesn't give me the exact same thing I started out with. It gives me the negation of it. So in other words, if I change x with negative x, I get negative y. Okay. Here are some examples. We're going to go ahead and play with those right now. And I'm going to work through, and we're going to determine the symmetries of each. Now, there's a long way to do this. There's a really fast way to do this too, and I'm going to share that with you. It's kind of my go-to because I do want you, say you're taking an SAT or a calculus AP test or something like that, I want you to have a little bit of an idea as to what's going down here. Notice this term odd function. And again, f of x is just like saying y equals. Notice the y has a power that's odd. It's to the first power. The x cubed has an odd power. The x has a power of 1, which is odd. So what I see as an odd function has all odd powers. That can help if you're given a polynomial such like this. I mean, when you're given other examples of different functions, you know, like an absolute value or something like that, it may cause some problems. But basically, if it's a polynomial and every term has odd powers, I know it's an odd function, in which case I know it also has origin symmetry. Let's go back to the other one. An even function, you know what? Let's look at the powers. I'm not going to worry about the y, but specifically I want to look at the x's. Even power, this is just y. So basically, if all of my x's have even powers, it's an even function, and it has y-axis symmetry. Just a little bit of some stuff that may help you doing a problem like this. So if I'm looking at problem A, right here. Okay, so let's go ahead and take a quick look here at part A. I'm looking at the exponents. I see that not all of them are odd, so I can pretty much cross out odd functions. So in other words, the three symmetries I'm looking for are y-axis, x-axis, and origin. And remember, origin is an odd function. Y-axis is an even function. So since I look and while the y does have an odd power, not everything does, so I'm pretty sure it's not origin symmetric, or I'm pretty sure it's not an odd function. But let's check out the y-axis symmetry. So for y-axis symmetry, I'm going to replace every x with a negative x, which gives me, well, a negative raised to an even power. Gives me a positive. And then I have a minus 5 here. And then we'll see what happens here. A negative x squared becomes a positive x squared, and a positive times this negative stays negative. And plus 3. How does this compare to what I started with? Well, quite favorably, actually. I can see that I have exactly the same thing that I started out with. So I'm feeling really good that this does have y-axis symmetry. Now, here's a question you might have. You say, but I thought y-axis symmetry meant that it was an even function. It does. If you say, well, all the powers aren't even, aren't they? Again, for an even function, I'm not worried about the powers on x or on y, just on the x. You say, see, this 3 doesn't have an even power. It's an odd number. Well, I want you to examine this thing. X to the power 0. Hopefully you remember in your Algebra 2 class that whenever you take something to the power 0, maybe you had a little post that said a to the power 0 equals 1. So this is really 3 is like saying 3x to the 0, and 0 is an even power. So you say, no, it can't be even. By definition, an even number is anything that can be divided equally by 2 without a remainder. And I could absolutely take $0 and share it evenly with 2 of you. Now that would mean that none of you get anything, but this does have y-axis symmetry. Now it is possible that some equations could have more than one, so let's also test for x-axis symmetry. X-axis symmetry means, again, my original was x to the 4th minus 5x squared plus 3x, or 3, I guess. Or you can call it 3x to the 0 if you want. So for x-axis symmetry, I'm going to replace the y with the negative y, which gives me negative y equals x to the 4th minus 5x squared plus 3. Does this look exactly like that? No. So this one only has y-axis symmetry. Now you might say, well, if you look, this side's exactly the same. Yeah, but is this side exactly the same? So the answer is no. Okay, let's continue. Okay, part B. I have y squared. Again, I'm looking for 3 things. I'm looking for y-axis, which is an even function. I'm looking for x-axis, which isn't a function at all. And I'm looking for origin symmetry, which is an odd function. And both of them start with O, if that helps. So I'm going to look at the powers. Origin symmetry, are all the powers odd? Well, 12 is really 12x to the 0. That's even, that's odd, that's even. So a little even and a little odd means I can cross out origin symmetry right now. Now, if you want me to test it, I actually will test it. If I'm going to test for origin symmetry, I'm going to replace both y with negative y and x with negative x. And again, I don't need the x to the 0. I can put it if you want, but And let's see what happens. Well, that's going to turn that y squared right back into positive again. That's sweet. But yeah, no. If some signs stay the same and some don't, that tells me the origin thing's really bad. And again, this is something I knew before I even started, just by analyzing the powers of the exponents, or the powers are the powers of each of the terms in the polynomial. Now, let's look at an even function here. Again, 12 is 12x to the power 0 by definition. That's the same thing. So I know that 12 does have an even power, but this, no. So I'm pretty sure this does not contain y-axis symmetry either, but I can check. So for y-axis symmetry, I'm going to replace every x with negative x, which gives me y squared equals negative 4x minus 12. Is this identical to that? Methinks not. So cross that out. So I'm feeling pretty good about this one probably being x-axis symmetry, unless your teacher's a real jerk, much like I am, who might give you one that has no symmetry at all and make you test them all. But let's test it for x-axis. By definition, an x-axis means every y changes to a negative y, and everything else stays the same. When I square negative y, that gives me y squared. It's 4x minus 12. How does that compare to the original? Quite favorably. So x-axis symmetry, yep, it's got it. Hopefully you kind of get the idea of what's going on. If you want to kind of pause and work through each one, you can. I'm not going to go through each and every test. Actually, I'm going to do it one last time here. Again, 5x is like saying 5x to the 1, if that makes you happy. Again, we're testing for y-axis or even functions. We're testing for x-axis. And we're testing for origin symmetry, which is an odd function. And just looking at it, again, 5x is 5x to the 1. That's odd. That's odd. Y to the first is odd. I am pretty much 99.999% sure this thing has origin symmetry. Let's test it. Remember, for origin symmetry, you're going to replace x for negative x, and y is going to become negative y, and let's see if it's the same we started out with. So that gives me negative y equals 10 times negative x cubed minus 5 times negative x. The result, negative y equals, well, put the cube out here. When I cube a negative, it's going to become negative, and then that's going to turn positive. So I check, is this identical to what I started with? No, it's not. So you say, oh no, but it should be origin symmetry. Mr. Winter, you promised it would be origin symmetry. It actually is. You know how if you're doing like an equation like this, if I have like 2 plus, let me rewrite that. If I have like 2 plus x equals 5, you know, I can like subtract 2 from both sides. In other words, it's legal to do something to one side of an equation so long as you do the exact same thing to the other side. Let's use that in figuring this out. So here's the idea. It doesn't look exactly like what I started with, but is it because some signs changed and some signs didn't? If that was the case, I would guarantee that symmetry would fail. No, it's a case where each and every term changed signs. So what can I do? Well, I can take this left side by negative 1 I can take the right side and multiply it by -1. Is it legal to do? Yeah. When you're solving equations, when you're working with equations, you can do whatever you do to one side so long as you do it to the other. So that turns that into a positive y. Distribute your -1, and that's a 10x cubed minus 5. And now, oh yeah, or odd function it is. This thing does possess origin symmetry. I'm not even going to bother testing for x-axis or y-axis because remember that's an even function and there aren't any even powers anywhere to be found. And then likewise, x-axis, you know what, I will test for x-axis. But again, just by the fact I've done so many of these over time, I know it's going to fail. But it doesn't hurt for you guys to get the same practice I've had. So again, I guess I kind of messed up this equation. Again, it was y equals 10x cubed minus 5x. So again, for x-axis symmetry, I'm going to replace y with -y. Which gives me -y equals 10x cubed minus 5x. Does that look exactly like what I started with? I'm feeling not. Now you may say, but what about like we did in the last one where we multiplied everything by -1 and it was okay? That worked because it was a situation where every single sign changed. So multiplying every term by -1 will turn them all back. Here, the only one that didn't change, see, looks like these stayed the same, but the y's didn't. So some signs changed, some didn't. I don't think that's going to make a difference here and turn it back into what it was. Actually, I'm 100% sure it's not. You say, can we try it anyway? Sure. Let's take that -y equals the 10x cubed minus 5x. And let's just go ahead and multiply everything by -1. Again, legal to do because it's an equation. You say, see, look, it turned that back into y. Yeah, I know. But at what cost? While it did turn the y back into itself, it kind of screwed up the others. So this one only has origin symmetry. Okay. Now, a couple of ways you can do this. Easy way is, I don't know how well you know your parent functions, but I know the graph of y equals 1 over x is a hyperbola that looks something like this. And I can tell you just by that, it does have origin symmetry. That is the graph of y equals 1 over x. Now, if you didn't know that, let's do another thing. Hopefully you remember like what negative powers do in algebra. Like if I had 2 to the -1 power, it makes it the reciprocal 1/2. So this equation right here could actually be written as y equals x to the -1. -1 is an odd number. 1 is an odd number. All powers are odd. That tells me I'm going to have origin symmetry. If you want to test it, again, I'm hoping that what you can see is what's going on before you actually find it. So if I want to test it for origin symmetry, I will replace y with -y. I will replace x with -x, which gives me -y equals -1 over x. So yeah, see, the origin didn't work, didn't it? This term on this side, the left, changed sign. The term on the right changed signs, so every term changed signs. So I can multiply everything by -1. Giving me y equals 1 over x, which is what I started with. So another technique you can use to determine origin symmetry. Now, okay, so we've established that it has origin symmetry. I get that. But what about the others? Well, again, let's think about the other types of symmetry. We have y-axis, which is an even function. And if you look at these powers, y to the first is odd. This x on the bottom has a power that's odd. There's no even powers in this thing at all, so I know how that's going to play out if you wanted to test it. To test for y-axis symmetry, I'm going to replace x with negative x, which gives me something that looks nothing like what I originally started with. Some signs changed, some signs did not. So some change, some don't. That means a lot of nothing. And then if you wanted to test for x-axis, that's where I would replace the y with the negative y and leave the 1 over x from the original problem alone. Gives me negative y equals 1 over x. These signs didn't change. These signs did. Some changed, some did not. Nope. So I know the only symmetry we have here is origin. Okay. Look at powers here. Again, we're testing three things. I'm testing for y, testing for x, testing for origin. Origin is odd. Y-axis is even. So I look at the powers. That's an odd power. That's an odd power. So right now I'm feeling that even isn't going to happen. Oh, that's even. And likewise, this 7 is 7x to the 0. So I've got some even and some odd, which means it's neither odd nor even. So the only type of symmetry this could possibly have would be x-axis. So let's test it. So I'm going to replace the y with negative y. And the x with the negative x. And again, 7x to the 0 is just 7. So that gives me negative y. A negative to an odd power is negative. A negative squared is positive, so that's plus 4x squared minus 7. So let's compare this to the original. Well, are they exactly the same? Well, the 7 has the same sign. The 4x squared has the same sign. That's good for us. Ooh, the x's. They changed. The y's changed. So half of the terms stayed with the same signs. The other half changed. And again, some change, some don't. Wah, wah. This does not have either of these symmetries. So this one has neither x-axis, y-axis, nor origin symmetry. Which can happen. Okay, problem F. Again, really easy to do if you know your parent functions. And hopefully from Algebra 2 you remember that the graph of y equals absolute x, or the absolute value parent function, looks kind of like a V, slope of -1 going left, slope of 1 going to the right, and passing through 0, 0. And I can see right here, right now, this sucker has got y-axis symmetry. I am 100% locked in on that. You say, but it doesn't have even powers. Okay, problems like this where it's not a polynomial. You know, polynomials when you have like something x cubed plus something x squared and x's and numbers, where it's just powers, no funky division kind of things, no absolute value symbols, for instance. Yeah, when that happens, I mean, when you have the polynomial, yeah, look at the powers. It's a great technique. But here, no. And you say, well, what if I didn't remember what the graph of the parent function for absolute value looks like? Okay, we'll do each test. So we'll test y-axis, which means I'm going to replace x with negative x. You say, aha, they're not the same. See, look, they're different. No, think about what absolute value is. Absolute value measures your distance from 0. So if I were to go like number line, the point 1 has a distance from 0 of 1. Likewise, the value negative 1 also has a value of 1 from the origin. If I go out to 7, or like even 72 for that instance, 72 is a distance of 72 from the origin, or from 0. Likewise, negative 72 has an absolute value or distance of the origin from that. So in other words, I know that the absolute value of 1 is equal to the absolute value of negative 1. I know the absolute value of 72 is equal to the absolute value of negative 72. In other words, I know the absolute value of negative x is the same as the absolute value of x. So this is really exactly the same thing I started out with. Okay, both x and negative x are the same distance from 0. Is this working okay for you now? All right. I can test the other ones if you want. They're going to crash and burn. Again, I know what the graph looks like. I've tested it. And again, think of it this way. I know that this absolute value will turn a negative x into a positive. What's going to happen to the y? Well, it's just if I change the sign of y, it's not going to turn back into a positive. And if I change both, the x will go back to what it started with, the y won't. So that is pretty much what you got going on there. I don't know if this helps you or not, but it's certainly here for you to use. If you want kind of a little guide here to go by, here's a little chart that I found that may help you guys too. Like what the different symmetries are. How do you test? You know, what do the coordinates look like? X, negative, xy, negative xy, and so forth. And then how you test algebraically. If that helps you out and you want to write that down, by all means, feel free to do so. That's why I put it in here. Okay. Next one, let's take a quick look at it and see what happens. Again, I'm looking for odd, even, or neither. So I'm going to look straight at the exponents. Y has an odd power. X to the 5th is odd. X to the 3rd is odd. 2x is 2x to the 1st. That's odd. So without going through and doing all those tests that I'd been doing, I will 100% guarantee this is an odd function. Here, odd power, even, and then that's x to the 0, which is also even. So when I'm testing for an even function, I don't worry about the y. I worry about the x's, and all of the x's have even powers. This is an even function. Here, odd, odd, odd. 1, while 1 is an odd number, it's really 1 times x to the 0, which is even. So some odd, some even means a lot of nothing. This is a neither. And then there's this last guy. He's going to be a pain. So this one we're going to actually work out. Now, I can do kind of an educated guess on this if I want to, in that Let me show you here. Okay. What I'm thinking of here is this. What's going to happen here if I take y and change it to negative y? Well, that's going to change the sign on y. And then this will stay exactly the same because there's no y's in it. So some signs change, some signs don't, which means if I change y for negative y, it doesn't work, which basically means I know it is not x-axis symmetry. I guess that wasn't even something I asked, but what's going to happen if I do this? What's going to happen if instead I change the sign on this x to negative x? Well, that's going to stay the same because I didn't change it. The 25 is going to stay the same. This x right here, when I turn it to negative x, will turn right back in. So I have a pretty good suspicion that this has y-axis symmetry, and as a result is an even function. Let's test it. So I'm going to take y equals square root of 25 minus negative x squared. Again, I'm doing the test for y-axis symmetry. I'm replacing x with negative x. The 25 stays. This negative right here may or may not stay because, let's see, a negative x squared turns positive, and then positive times a negative. I see that's exactly the same thing I started out with, so this is an even function. Okay, let's test it to see if it's an odd function. Again, I'm not just going to use the powers because, you know, it's funky. It has that square root. So if I change the y to negative y, and I change the x to negative x, which is my test for an odd function, which is origin symmetry. So this one's good. We'll see what happens here. Well, that's going to change to a negative y. 25 is the same. A negative x squared is positive times this negative. It's negative, so the signs on the square root part were the same, but the signs on y, no. So part D only has, it's an even function. Okay. I want to finish up just doing two last quick things. I want to take a graph here, and let's just complete a graph. So here I have a graph. It's actually a graph of y equals sine x. Or actually it has an amplitude on it, like 1, 2, 3, 4, like y equals 5 sine x, but that's not important. What I want to do is just complete the graph of this function so it fulfills the following condition. I want it to be an even function, which means I want it to have y-axis symmetry. Does it look like this y-axis cuts that into two equal parts? I'm going with no. So what I'm going to do is construct it so that it does. So basically I want this to be like a mirror. And when it looks in the mirror, like this point right here should see itself. It's like almost 2 comma something, a little bit short of that. Should look something like this. In other words, 1, 2, just a little bit past 3 it crosses. So should look something like this. And then it figures out at like 4 or 5. Should look something like, again, being artistic is not a strength of mine, but now at least I've shown, despite my limited artistic ability, I've shown that the y-axis appears to cut it in half. Let me draw it again without the axis here. So basically, this point's reflected here. This point's reflected like here. This point is reflected like here. So it goes something like that. All right, last one. I want this to be an odd function. Again, what does an odd function have? It has origin symmetry. Here's the origin, which means I want this thing reflected right over here. So it would look something like, well, that. Now it's completed so that it would possess origin symmetry. Hopefully this makes a little bit of sense to you. And again, I hope you learned something. Enjoy.